Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to carry out implicit differentiation. Before we get started, let's take a look at what the term implicit differentiation means. To do this, we're going to take a look at what an explicit and an implicit equation looks like when differentiating with respect to, let's say, x, for example. Okay, so let's say when differentiating y with respect to x, an explicit equation is going to be something like this. An explicit equation will be something like y equals x squared plus 3x. Now, what makes this equation an explicit equation? It is an explicit equation when we're differentiating y with respect to x because y, the variable you're differentiating, is isolated. Okay? Now, that's case A. Case B, an implicit equation, which is why we are studying implicit differentiation. An implicit equation, when you're differentiating y with respect to x, looks something like x squared plus 3xy plus y squared equals 5. Now, what makes this equation implicit? It's implicit because y is not isolated. Okay? So whatever variable you're differentiating, if that variable is isolated in the equation, it's an explicit differentiation type scenario. But if it's not isolated, then it's an implicit differentiation. Okay? So that brings up the question, why study implicit differentiation? So why? That's the question we're going to address now. A lot of times, it's easy to isolate the variable you're differentiating. You can convert an implicit equation to an explicit equation and then differentiate. But there are many times where your equation, considering your current knowledge of mathematics, you might not be able to isolate the variable you're differentiating. Okay, so in cases like that, it's impossible to find the derivative if you do not know the implicit differentiation technique. Okay, so why study implicit differentiation? The reason is as follows. You can differentiate an equation regardless of if the variable you're differentiating is isolated or not. Okay, so that saves you time, and also that saves you the ability to find the derivative. Okay, so if you find a situation where you can't solve an equation for y, for instance, for example, in this case right here in the part B, you can't solve for y, but you can still find the derivative with the implicit differentiation technique without even wasting your time trying to isolate the variable you're differentiating. Okay, so that's basically why the implicit differentiation technique is extremely important and powerful. Now let's go ahead and take a look at some examples. So the instructions for the examples we are doing is to find the derivative of y with respect to x. Okay? All right, number one, what if we have the equation x squared minus 5y squared equals 2? Now, whenever you're differentiating implicitly, as is the case here, there's a word you want to keep in mind, which is, the word is agreement. Okay? what you're differentiating with respect to, does the variable you're differentiating agree with it or not? That's something to keep in mind. Now let's go ahead and differentiate, and I'll show you what agreement and disagreement mean within the context of this problem. First of all, is this an implicit equation? It certainly is, because y, the variable you're differentiating, is not isolated. Okay, so we're going to use implicit differentiation here. So we're starting with the equation x squared minus 5y squared equals 2. All right, so let's go ahead and differentiate. We're going to be finding the derivative of each term, so derivative of x squared minus the derivative with respect to x of 5y squared, and then the derivative with respect to x of 2. Okay? All right, let's take a look at the first one. So when you differentiate x squared, you might have studied the power rule. The derivative of x squared is 2x. But I'm going to add on something. Using the chain rule, we're going to have 2x dx dx. d of the variable you're of this variable with respect to the variable you're differentiating with respect to, okay, which is x. All right, so it's 2x dx dx minus, now let's differentiate this. We can factor out the 5. The derivative of y squared is 2y, using the power rule, dy dx. Okay, and then if you differentiate, 2 is a constant, so the derivative is going to be 0. Now let's talk a little bit about agreement real quick. Now if you notice, this dx dx, they are identical, so what happens? It divides out to 1. This indicates agreement. Okay, so this is agreement. So if the variable you're differentiating is the same as the variable you're differentiating with respect to, there is going to be agreement. So you will not have d of that variable dx, because they're going to divide out. But in this scenario right here, y and x are different. Okay, that indicates disagreement. Disagreement. So when you're differentiating a variable and it's different from the variable you're differentiating with respect to, you have to use the chain rule and apply d of that variable, d what you're differentiating with respect to. Okay, so always check for agreement when you're differentiating implicitly. All right, so differentiating x squared gives us 2x. We do not have d anything dx there because there's agreement. Minus 5 times 2 is 10y. The derivative of y squared is 2y times 10 is 10y. But since there's this agreement, we have to reflect that by indicating dy dx. Okay? And then the derivative of 2 we found out was 0. Alright, so that's how you differentiate implicitly. To finish the process off, we're just going to isolate the dy dx component, or just use the processes of algebra to accomplish that. Okay, so we'll subtract 2x from both sides, and then we have negative 10y dy dx equals negative 2x. And then to finish things off, we'll just divide by the coefficient of dy dx, which is negative 10y. Apply that to both sides. And your final answer, dy dx, is going to be x over 5y. Okay, because the minuses divide out, and then 2 goes into 10 5 times. And ladies and gentlemen, that's the derivative of y with respect to x for equation in question number 1. All right, let's go ahead and try another example. Question 2. Let's say we have the equation 3x plus 4y equals negative 4y squared plus 3. Okay, so we are still finding the derivative of y with respect to x. So we have 3x plus 4y equals negative 4y squared plus 3. Now, what do you keep in mind when you're implicit differentiating? When you're carrying out implicit differentiation, don't forget the word agreement, okay? So, there's agreement with the 3x, and this is a constant, so that always agrees. So let's go ahead and differentiate. When you differentiate 3x, you have 3. Dx, you don't have to put anything there since there's agreement. With the 4y component, there is disagreement. Y and what you're differentiating with respect to x are different. How do we reflect that? Differentiate this first, 4, and then reflect the disagreement using dy dx. Okay, this is basically the chain rule. You're working your way from outside all the way in. We have another term where there's disagreement, so we're going to differentiate with respect to x. We're going to have a dy dx component attached to it, so let's differentiate. We're going to have negative 8y, and then we're going to illustrate or reflect the disagreement by adding on dy dx. Okay, derivative of 3 is a constant, so the derivative with respect to any variable is going to be 0 since constants never change. Okay, now we're done differentiating. What we're going to do now is we're going to collect all the terms with dy dx to one side, and every other term goes to the other side, and then we'll factor out dy dx and have it isolated. So let's go ahead and collect all the terms with dy dx. So we can just subtract 4 dy dx from both sides just to save time. Okay, and then we're going to have 3 equals negative 8y dy dx minus 4 dy dx. Now, why are we collecting all the terms with dy dx to one side of the equation? Well, that enables us to factor out dy dx. So watch this, dy dx can be factored out. So we have negative 8y minus 4. Factor out dy dx. Now we can proceed to have it isolated. We'll divide both sides by the coefficient of dy dx, which is negative 8y minus 4. So divide both sides by negative 8y minus 4. Alrighty, and then your final answer is going to be dy dx, the derivative of y with respect to x, equals 3 over negative 8y minus 4. Or you can also write this as dy dx, if you factor out the minus from the bottom, equals negative 3 over 8y plus 4. So these are just two ways of writing exactly the same answer. Alright, let's take a look at question 3. The nice thing about question 3 is that it helps us to see how implicit differentiation can be used. It can be used to find the equation of tangent lines to curves that are not functions. Okay, so the instructions for number 3 are to find the equation of the line tangent to the given curve at the specified point. Okay. All right. So let's go ahead and consider the equation. The equation is 4 equals 2x plus 3y plus 3y cubed, and the point of tangency that we want to find equation of the tan line 2 is negative 1 comma 1. Okay. All right, let's go ahead and do this. Now, when we're looking for the equation of the tangent line, we're going to be using the formula. So formula for equation of tan line, y minus y1 equals m x minus x1. Oh wait, look at this. This is a algebra 1 or 2 equation, right? Equation of the point slope form of the equation of a line. So this is the algebraic variation of the formula we're going to be using. In this particular case, m is going to be dy dx, the derivative evaluated at the point of tangency x1, y1. Okay, so a more advanced notation is basically f of x minus f of a equals f prime of a times x minus a. Okay, so these two equations are basically the same thing, but the one on the left is much easier on the eyes, but you can also use the one on the right. It doesn't really matter. Okay, so I'm going to use the elementary equation, the simple approach here. So all we just have to do is find x1, y1, and m, plug it into this equation, the point slope form equation of a line, and we're good to go. Okay, now let's see what we have. We know that x1 is the x coordinate of the point, -1, that's easy. y1 is 1, that's easy. What is m? M is the derivative evaluated at the point of tangency -1, 1. Finding the derivative at a point, or you can also use this notation is good. Finding the derivative at a point is a two-step process. Okay? In this particular problem, we're going to have to first of all find the derivative of the equation. Since this equation we're looking at is not explicit, that means that implicit differentiation will be used here. And then after implicit differentiating, part 2, we're just simply going to evaluate the derivative at the point of tangency, which is -1, 1. So it's a two-step process. Okay? Alright, so let's start with part number 1, which is to find the derivative of our implicitly defined function. So it's not a function, it's a relation. So number 1, part 1, we want to find dy dx. Okay, so the equation again is 4 equals 2x plus 3y plus 3y to the third. Now, what word do you want to call to mind when you are differentiating implicitly? You want to remember the word agreement, okay? So when you're differentiating, these two terms here are not in agreement. So please, please, please do not forget to add on dy dx to both of them when you differentiate. Alright, but the other ones, this is going to be 0, so it doesn't matter. And this one agrees, so you don't have to add anything on there. Okay, so let's go ahead and start differentiating, keeping the word agreement close in mind. The derivative of 4 is 0 because a constant. Derivative of 2x is 2. Agreement, dx is gone, plus the derivative of 3y is 3. Since there's disagreement, you add on dy dx. The derivative of 3y cubed is 9y squared, applying the power rule. There is disagreement, so we add dy dx. Now that we're done differentiating, we have to collect all the terms with dy dx to one side of the equation, factor out dy dx, and have it isolated. So we can just minus 2 from both sides of this equation to accomplish that desired form. If we switch the equation around, we're going to have, well, let's not switch it around. I just want to show you something real quick. When you cancel this out, subtract that from both sides, I can factor out dy dx. Okay, so we have 3 plus 9y squared. Okay, factor out dy dx. Last step, to isolate dy dx, we're going to divide both sides of the equation by what? The coefficient of dy dx, which is 3 plus 9y squared. Do that to both sides of the equation. So this divides out. And then we have, what do we have? We have dy dx slope at any point on the curve is negative 2 over 3 plus 9y squared. Okay? Alright, now we are done with part 1. Now we need to do part 2. Remember what part 2 is? Part 2 is to evaluate. So part 2, we're going to evaluate the derivative at the point of tangency at negative 1 comma 1. Okay, so let's go ahead and do that. We're going to have dy dx evaluated at negative 1, 1. This simply means plug in negative 1 for all the x's and 1 for the y's. This equation is only dependent on y, so we're going to substitute 1 for y. So 3 plus 9 times 1 square. Okay, it's not dependent on x, so we don't make use of the negative 1. Let's simplify. We are going to have negative 2 over 12, which reduces to negative 1 over 6. So this is the slope of the tangent line to the curve at point negative 1, 1. Okay, so we now have m. Remember, x1 was negative 1 and y1 is 1. We have all the ingredients that we need to put into our recipe, the point slope form of the equation of a line, to generate our desired line. Okay, so we have y minus y1 equals m, the slope, times x minus x1, minus minus plus, like that. Okay, if we want to get y isolated, so this is one form, this is the point slope form. If you want to put it in slope intercept form, you just get y isolated. Okay, so let's do that real quick. So we can have y minus 1 equals negative 1 over 6x minus 1 over 6 if you distribute, and then you can add 1 to both sides, but 1 is the same thing as 6 over 6, so you can just add 6 over 6 to both sides, and then you have the slope intercept form, which is y equals negative 1 over 6 plus negative 1 over 6x, let's not forget that, negative 1 over 6x plus 5 over 6. Okay, so that's the point, the slope intercept form of the equation of the tangent line to the curve at negative 1, 1. Alright, so how well did you understand the material we just covered, the art of implicit differentiation? To demonstrate mastery, we'd like you to try out the following problems. So basically, you just copy it down, pause the video, work through all of them, and then reinitiate playback to see what the answers are. Okay, so instructions for problems 1 to 4, you are to find dy dx using implicit differentiation. Okay. Number 1, what if you have the equation 2x squared minus 3y squared equals 4? Number 2, what if you have 1 equals 5x to the third minus 4y squared? Number 3, what if you have x equals negative 4y minus 3y squared plus 5? Number 4, what if you're given 4x to the third plus 2y squared equals negative 3y plus 1? And then for number 5 and 6, you're to write the equation of the line tangent to the curve at the point, okay, at the specified point. All right, so for 5, let's say you have the equation, let's see, 5, you have 2x plus 2y squared equals negative 3y plus 3 at 2, negative 1. And then for number 6, let's say we have the curve with equation 3x to the third plus 5y to the third plus 5x equals 3, and the point is 1, negative 1. Alright, so go ahead and pause the video at this time and try these problems. When you're done, just click on play to see what the answers are. Okay, so hopefully you had a chance to try the problems. The answers are as follows. For number 1, the answer dy dx is equal to 2x over 3y. For number 2, dy dx is equal to 15x squared over 8y. Number 3, dy dx is equal to 1 over negative 4 minus 6y, or you can write it as dy dx equals negative 1 over 4 plus 6y, same thing. Number 4, dy dx is equal to negative 12x squared over 4y plus 3, or you can have dy dx equals, if you distribute the negative to the denominator, you have 12x squared over negative 4y minus 3. Okay, and then for question 5, the equation of the line, the tangent line, is y plus 1 equals 2 times x minus 2. And then for number 6, the equation is y plus 1 equals negative 14 over 15. Negative 14 over 15 times x minus 1. Okay, so there goes all the answers. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your studies of implicit differentiation, to give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments, just place it in the comment section below and we'll be more than glad to assist you. Don't forget to subscribe to our channel for updates to other calculus tutorials such as this. More clips, tutorials, and support resources can be found at mathgotserved.com. Go ahead and check it out. Thanks again for watching and have a wonderful day. Goodbye.